Okay, I think we're going to get started. I think it's on time. Okay, so my name is Xingjun, and I'm a senior research engineer working for Huawei Enterprise Business Unit. This is my colleague, Guoli, and he's the chief architect of DC Network, also within Huawei Business Enterprise Business Unit. So we're going to talk about the FaaS, Fabric as Service. It's a project within the ODL community. So Guoli is going to cover the concept part. So I'm going to talk about the project specific aspects.
Okay, thank you.
Okay.
Okay, I'm more talking about where the project come from and why, and the talk come from what kind of business case and the user case. Every year I contact a lot of customers. So this project basically is come from the customers and the users. This is a typical data center network. Because the history reason, customer build such kind of network. In this network, there are a lot of port because a lot of reason. For example, like physical limitation, space limitation. So they build one port by one port. And because history reason, they use different technologies. For example, in the beginning, they use MSTP. Then later, they use Fabric PaaS. Then they use Trio, use NGRE, use VXLAN. And every time, they build one port, one by one. Also, because the vendor reason, so they try to build different network, different port, come from different vendors, try to compare their support, their technology, their products. So with this reason, they build this also include another reason, it's a service reason, because they want to isolate their service for different service put on different port. So this is formed this network. This physical network, you can see this physical network has a lot of technologies, a lot of domains in here. It is exactly like current in the key sessions, keynotes. We can see we are talking about a lot of controllers, SDN controller, SDN WAN. In here, from business perspective, customer doesn't care about the DCI from service perspective. But the DCI is in there, WAN is in there. Everything's from customer perspective. I just wanted to see where is my CPU resources and where is my storage resources. Even they are in different locations. My task is try to build it up and provide services. So right now you can see in the keynotes, we are talking about a lot of controllers. That's why a lot of controllers come from. And in this project, we try to eliminate this confusion because it's come from customer requirement. Customer can ask us a lot of things, not just focus in here, also focus on in the middle, access core. They call that one as the SDN network because they already build some services in here and some new services in here. The problem for them is how can I create end-to-end paths? That path probably cross over several physical networks. For example, like I already have provided database services in here. So some new apps I try to put it in here. User come from internet or from VPN that come from another network, use different technology. How do I create end-to-end path? That path will cross over several physical network domains. How do I do that? So this is, I contact a lot of customer, visit it. 99% daily job is try to create these connections. So that's the project come from. So first, we try to solve network dependency, which means each port in here, each fabric could use different technology. For example, MSTP, VXLAN, you could use centralized control like normal SDN controller or open floor controller. It could be overlay or underlay, doesn't matter. It could be used, they come from different vendor, doesn't matter. But the thing is each port in here, each fabric right now is strongly depends on vendors, depends on technologies, depends on topologies, depends on a lot of things in here. We try to modularize the network, try to solve this problem. On the northbound, provide a unified interface. Let the customer, when use this network, feel like I just try to deal with one type of the network. One thing. Second thing is we try to solve end-to-end connectivity issues. We know in this port, it's just most of the case, you just connect it with CPU resources and storage resources, but you don't connect the user, which means user could come from different network. For example, from VPN, from internet. They have different entries from here. So we need to connect them together, not just the CPU and the storage. We need to connect to the user. Now, how to do it? Third one is security. Very funny things right now is looks like everyone just thinking about one port and put everything in here. That include your web tier, your app tier, your database tier, everything's put in one. But on the real situation, nobody do that. Each components, each tiers has different security level. They should separate it and put on different security. We call this port, security zone, or whatever you name it. This is, I just talk about this one. Right now, a lot of things just put in here because your VM, different companies, different applications, VM share the same physical servers. Probably caused a lot of security issues. For example, like side channel attack, they take the advantage of the cache in the server and try to attack each other. So normal cases, they will put on the real cases, they will put each tiers on different service zone, try to separate it. Also, even in one port, even one physical server, they have different port. For each different port, they have different security level. For example, like this is a typical physical server. We have console port. This is the highest priority port used to control all physical servers. After this port decide what kind of platform you want to install. For example, I installed VMware or OpenStack. Then you generate management port, which is this port. So they are on different security level. You should isolate it. Cannot put them on the one network because the services. Then after you install the VMware or OpenStack, then you have data port, which will let users' traffic go through it. So even one physical server in one port, there are several networks. You need separate them, isolate them. So what we are doing in this project, first we try to modularize each fabric. So the network will becomes modularize the network. So when you, in the system perspective, when the network changes, well, we always say there's no final technology in the network world. The network always changing. So to solve this problem, all the networks have to be modularized. If you change one, just change one module and not affect the other parts. So first things is modularize the network. Second is to create an end-to-end path, which means I create a path from internet or from VPN and cross different physical network, create end-to-end path. Third of things is we need resource segmentation, which means even in one physical port, we need separate the resources. Let each CPU has its zone and there's no crossover. When you try to from one zone to another zone, you need to pass some policy rules. Here is what we do. So fabric definition. A fabric definition is one fabric is under one controller or under one protocol, which use the same way to manage your resources and to control your resources, to assign your resources, to manage your resources. It doesn't matter it's centralized or it's distributed. Just one, for example, VXLAN is a one fabric. STP could be another fabric. It doesn't matter. It's like you buy a switch. Some switches has bad, very good, better backplane, and the switch fabric. Someone doesn't have it. Someone has a block. Some switch doesn't have block. So we try to use this method to high NI information, high topology information, high encapsulation information, vendor information, because for all the fabric from the service provider, from service perspective, they provide the same services. For example, all the protocols follow ISO 7-layer model. So all the networks provide layer 1, layer 2, or layer 3, this kind of services. This is basic functionality of the network. So each fabric has its fabric controller. It's focused on connectivity of the NI. So between this fabric controller, we have fabric manager, which use to create connections between these fabrics. So which does a very simple job. It could be centralized, could be distributed. If you use distributed, common case is use BGP VPN to connect all the fabric together. After use this concept, so the network looks like very simple. So each fabric connect to a lot of servers, storage resources, firewall, load balancer resources. And from your customer perspective, I only see a device in here. We call this fabric. I didn't see the inside, what kind of topology it is, what kind of technology it is. I just see a fabric. So now resource segmentation becomes easier. Whole network are poured physical network port that connect to a lot of storage, CPU resources, firewall, and appliance resources. It's connected to one fabric. And if I try to segmentation, I just split this fabric, becomes virtual fabric. So each resources connect to this vFabric. It belongs to the owner of this vFabric. So it cannot cross over. So the resource segmentation becomes very clear and very easy. For example, in here, this is a fabric. This is a whole resources. So I virtualize the fabric become here. So this part I give to user A. So this is user A can use what he can use. All right? Very easy, very clear. Also, the same way I can use the vFabric concept, provide management tool, management network for user B. And they will have very clear interface. And I give the logging the authority to manage this vFabric, then it's done by themselves. For APP deployment, it also becomes very clear. For example, I have this GBP applications. What I do is, I know it's come from VPN, so I need in that vFabric, I create a router, several routers in different vFabric, which means in different zones, right? This fabric is I give to this user, so this user can do whatever, use this, use given resources. Then I create another router to connect them together. It's done. So every tiers were sitting on different location. From customer perspective, I don't need to know inside of the fabric. Expect when something bad things happens, the network admin will follow this mapping relationship between vFabric and the real and the fabric, physical fabric, and check the real forwarding table. Now I give my colleague to the Xingjun, the detail.
Okay, thanks, Guoli. Yeah, so as Guoli talked about the fabric, he touched on the fabric from very concept level. It's very high-level vision. I'm just from another perspective talk about why we set up this project. As Guoli mentioned, the network, the physical network, including the data center network, because of adopting so many different technology from different vendor and using different kind of implementation. So the network becomes more and more complicated physically. And also there's, as Guoli mentioned, there are lots of new requirements from different perspectives put on the network. So not to mention traditionally when we provision network services or deploy new network services is already very labor intensive. It's for larger or bigger enterprise, you usually have two different departments, the IT department and the network department. So there also need some kind of translation between the APP requirements to the network terminology. Then when you provision the network, because of physical network complexity, so provisioning also is very labor intensive. So not to mention we entering the new computing era. So there's cloud computing and server virtualization, microservices, DevOps, those kind of new computing paradigm introduce more requirements on the network. You need network more agile and virtualized, support multi-tenancy, etc. So to make the network more programmable, it's become very, very urgent. If the status quo provisioning is okay, but now I think we cannot just wait. We have to keep up with all the server virtualization, new computing technology. So how do we solve the problem? I think we can learn something from how we program the computer. So historically, if you look at the last like 30, 40, or 50 years, when the computer technology advances, so in the beginning, we programmed the computer using the machine code, probably using the codes on the paper. Then later, we're using the assembly language, then C language, then high level like Java or Python today. So we keep adding new abstraction layers. Each abstraction layer absorbs lots of complexities. So that's why we making program computer is much easier. And every layer just focus on what they're good at it, right? Application developer, you just know the C language or Java language, the Python language. You don't have to know what's the processor, what's the operating system, and also what's the specific circuits or the physical the architecture of the computer. So same thing to the network world. Oh, sorry. If you look at today, everybody talk about the controller. It's very general architecture. You have the northbound, southbound. Then you deal with a bunch of network devices. It could be virtual devices. It could be network, the physical devices. But I think there's a big gap between the northbound and the southbound today. Everybody, if you look at the Neutron or GBP, for example, it's all from top down, from the user level, talk about the requirements. But how do you achieve that to program network? I think today there's we haven't seen a very concrete proposal yet. So that's why we proposed the FaaS project in last year, 2015, in the Bay release of ODL. So we try to just fill that gap. So the idea is very straightforward, okay, as Guoli mentioned before. So instead of dealing with the physical network, which composed of a bunch of different vendors, devices, and different technologies, we add an abstraction layer just on top of the physical network. So the fabric concept really comes from, it's not the new terminology. If you open up today's network box, there's a piece of hardware called switch fabric, connect all the interfaces on the device. That's the pipeline from, you get the ingress traffic, you do the layer 2, you do this bunch of table manipulation, then you do the ACL, then it goes from egress. So we just extend that concept from device level to a network level. Think about the network, right? It's really a bunch of devices connect to a bunch of interfaces. Just the interface is not on one device, it's across different devices. But the complexity is really because the device is not coming from the same vendor or implementing the same technology. It's a heterogeneous network. So we kind of, using this method, we kind of divide that heterogeneous network into a homogeneous, bunch of small homogeneous network. So if you look at each, some subset network, usually for each data segment, they're using the same data path or controlled by the same control plane, right? Then on the other domain, maybe you control. It's like the BGP protocol when you deal with different admin domain. So for that domain, the policy is kind of consistent. Same thing to the physical network. Some set of networks, they share the same technology, same data path, and same control plane. So as Guoli mentioned, we can abstract that part, to a fabric. So then we have a homogeneous network with a composed of bunch of fabric, other than consists of lots of different devices. And each fabric, it does the, similar things. If you look at today, it does, layer 2, you can create tunnel, you can create a layer 2 construct and the layer 3 construct. You can set ACL, and you can do some QoS. It's all common. Everybody does something, follow the RFC, just the interface could be different. So here example of the fabric we implemented in the FaaS project. It's we're using OVS. We implemented OVS VSLAN-based fabric. So within that fabric specific implementation, it has 3 layers. The top layer is very important. It has to implement very common services. Those common services has to be across different fabric. That common services make the fabric homogeneous. Within the fabric itself, usually you have to have managed the resource within that fabric. That resource could be technology specific. For example, for VSLAN, you have to manage all the VNIs. You have some layer 2 segment, layer 3, some ACL table to manage and port. And at the bottom, you need to manage all the devices which compose of that fabric. The interface could be, really depends on the interface, the devices, what the interface offer. It could be netconf-based southbound interface, could be OpenFlow, OVSDB, and some cases for some legacy devices using command line. But those specific details encapsulated within the fabric. From the top level, from the application level, you don't see that complexity. Okay, you only see the fabric offer services. You use that services to program network. So I'm not going to talk about too much details about how we implement those specific layer 2, layer 3 construct, because this is really up to the implementation. Those technology existing today. It's not like a new technology we invented because of this new project. We leverage all the new all the existing technologies which only been done in the last 30, 40 years to implement that. That's not hard. But the service model has to be common. This model we show here is not, I don't think it's a complete model, but it captures all the major constructs most of the user using to build a network, their services. So from the bottom, the endpoint really represents the machines you need to connect. Like server in reality, it could be a server, it could be a VM, it could be a Docker, a container instance. Then usually it's connected by a layer 2 construct, which we call the logical switch. Logical switch is just like a physical switch. It does layer 2 forwarding. Then you need the layer 3 connectivity. The layer 3 construct we call the logical router. The logical router connects layer 2. Those service model implemented on one fabric, but you have this topology which consists of a bunch of fabrics. You need if you have endpoints distributed on different fabric, you need to interconnect those layer 2 constructs on different fabric. You also need to interconnect all the layer 3 construct on different fabric. So that's why we have the construct like C4 and so those primitives services to make that happen. And of course, also you have the logical port. A logical port really represents the interfaces with attached different construct together. On the logical port, you can enforce ACL, the policy. And for the logical router, you need some kind of manipulation to the routing table. Okay, it could be automatically manipulated by the protocol. We can leverage like BGP or the existing protocol. The controller also can provision them. So this is the verse. This is the simplest, the most simple construct. As I mentioned, is a layer 2 logical network. You can connect a bunch of endpoints. So there are two ways you can attach the endpoint to the logical to the layer 2 construct. You either pre-configure some physical interface and bound that physical interface to the logical port, or you can register the endpoint. Those APIs really. We look at the current, the Neutron, and we gather lots of requirements. We think those two APIs can be converged into one, but I think it has its own use cases. So of course, layer 2 is not enough. Sometimes you have endpoints across different subnet. You need a layer 3 construct to connect the layer 2. So we have this logical router. So you basically you can, on the fabric project object, you can create a logical port, which is then you can create a gateway, associate that logical port with between the logical switch and the logical router. It does the layer 3 forwarding. So sometimes you need communicate with some external network, which is called external gateway. By external, I mean you have different IP domains, layer 3 contexts, like, for example, private IP and public IP. You need to convert those IP domains using some net functionality. So we have that construct to does that work. So then, as I mentioned, so this is another scenario. If you want to net, you also need some kind of other treatment for that traffic. For example, you need to go through not just net, you need to go through some kind of service function. We also provide that construct, so you can join your flow, the traffic, to an external logical port, which can go through some kind of service function and go back to the logical return. We did some integration with the service functioning project in ODL. So we can achieve that, but for now it's limited to just within that fabric. We're looking forward to get that done for multi-fabric as well. So as I mentioned, if you have endpoints which connect on different fabric, right? Then you create a layer 2 construct, connect the local endpoints. By local, I mean you have endpoints just within that fabric. But you need, but those endpoints on same subnet, you have to do some interconnection between the logical switch on different fabric. For layer 3 as well. So for the layer 2, basically this will give you a very simple example. If you have two fabrics with topology, topology they interconnect directly. I'm just give you the simple case first. Then I'm going to talk about the more general case. So for this case, it's very simple calculation. You know that you can from the fabric, the abstract topology, you get the path, you get the endpoint, you get the physical port which connects the two fabrics. Then you need bending that physical port to that logical switch you need to connect to. Then you set up the path between the logical switch. You interconnect them. And so you can do learning, make learning by itself if the fabric support that. Or you can use controller, just manipulate the MAC table to synchronize the MAC table between the switches on different fabric. For the layer 3, for the first implementation, we support two options. One, it really depends on the fabric itself. If they support tunnel capability, you can use tunnel to connect the layer 3 construct. Or you can just create another layer 2 construct which connects two layer 3 construct on different fabric. The difference is when you create layer 2, you kind of need you can consume some layer 2 resource, for example, VLANs, stuff like that. But for layer 3, you don't have that limit. But you have other limitations, but you don't consume the layer 2 resources. So here example, if you do layer 3 connection, you can set up a tunnel. Here the example shows we're using GRE. Well, this is a really internal implementation. From top level, you don't see that. You just create the logical port and bending the tunnel port bending to the logical router. You get that service, but within that we can set up the tunnel. But if a user has requirements, they want interrupt, they want to manipulate what technology they can use, we can make that exposed available as well. So this is the example for the layer using the layer 2 construct to connect the layer 3 router. Basically, you have to internally you create a logical switch, bending the logical port. Then you create a gateway, attach the logical router. And that way, you connect the logical. Then you have to using define the routing table. So this is the distributed gateway. So as I said, if you have endpoints distributed on different fabrics, and if you need to communicate across the subnet, but the destination is on the local fabric, you don't want the traffic hairpin to another fabric and go back. You kind of want, let's say, if you want the communication between the 192.168.3.3 to the 4.2, 168.4.2, you don't want to go to the router 1, then go back to the 4.2. You kind of want to go to the router 2 on that local fabric and go back to 4.2. So we have the distributed. So this is show the example how you using the construct the services we offer, how you create a distributed gateway functionality. So you have the optimal path. So this diagram is really talking about the general case. So for the layer 2 interconnect, as I mentioned before, I give you a very simple example. If the two fabrics topology physically is just neighbor, that's easier. But if they have some fabric in the middle, you have to. This is the layer 2. You have to calculate the path between the logical switch 1 and a logical switch 2. You want to interconnect. Usually, because it's a layer 2, you try to avoid the loop. You have to calculate a tree path. Then you have to create a transit logical switch on the fabrics in the middle. Then you're using the previous the steps to chain them together. So this is for layer 3. For the layer 3, the only thing is you don't have to care about the loop because you can always use the shortest path. You can also use ECMP to connect the layer 3 because it's a hop by hop routing. So then you calculate all the shortest path. Basically, it's a shortest path tree between the logical router constructs. Then you have to create the logical router on the transit fabric. By transit fabric, I mean in the middle, the topology. Then you create that kind of like a logical topology between the logical router 1 and logical router 2. Then using the previous steps to create to set up the routing table. So that basically just give you the example how you using those FaaS services to build the logical network. Doesn't matter if you endpoint on one fabric or on multi-fabric. So this just give you the overview of the FaaS architecture of this the software architecture. So we exposed a few northbound interfaces which has to different level. So we support the GBP as well. We have a GBP fast render. You can use the GBP fast render. So in that case, you can leverage the GBP model. It's automatically map the GBP model into the physical network. Or you can using logical network service, which is very similar to the neutron depth model. You don't have to care about how the endpoint distributed. So you can use that one to describe your requirements, and we can map that into the physical network configuration. Or you're directly using the FaaS service, as I mentioned before. All the constructs, you can write your own application. By looking at the abstract fabric topology, you can do your own traffic manipulation. You can control the routing table, the ACL, and where you want to put your transit logical switch, how you configure logical, using that construct, build your service. So, but that all the details, all the physical network or implementation details are encapsulated in that service. You don't have to directly using OpenFlow or netconf or command line to talk about different vendor devices. So far for the fabric, we have a framework. We welcome other fabric providers. You can implement using our example to implement your own fabric and plug into our framework. So in that case, we can support more different technology, different fabrics.
So just to add some comments. We had a lot of bad experience with our customer. The thing is, when you say current in the data center, if you only have one port, but basically when customers' traffic come from MPLS, from VPN, or from internet, the traffic will go through different paths and goes to like firewall or these appliances, then into your pod. So what the customer requirement is, I need end-to-end pass. So for this reason, we had a lot of bad experience to build a lot of vertical release. Then becomes each customer has one release because the customer pass from the MPS or VPN or from internet, it's come from different, they have different requirements for the firewall, for the load balance. So we build a lot of vertical release for this customer. So that's why this one is important. It's very close to customers' requirements. It's not just, if everything's put in one port, in the customer side, it's like a toy. You cannot really provide business services in there. Just to add one comment in here.
Okay, that's great. Yeah, so the Fabric as a Service really try to deal with the network with a more very generic way. We're not talking about specific open flow network or some vendor specific network. We really want have this methodology so we can have an architecture works for all the networks, not just one specific network. But to build that fabric, I think it needs more community collaboration to achieve that same goal. So that just give you an overview of the FaaS project we introduced in the Bay release. And the first release, we really focus on one fabric and the service definition. For the Boron release, right now we support multi-fabric mapping. So basically you can define, you can either using neutron logical network model or a GBP, we can map that into a multi-fabric topology. So I'm going to run a demo because I have a very tight schedule, so I'm going to run just video.
Do you have an example of what type of devices you use so far to configure?
Right now, we only support OVS. Yeah, Open vSwitch. Yeah.
You mentioned the logical router, so the logical OVS is the logical switch. Represented in the abstraction layer, right? Is the logical router some software that runs the controller?
No, logic, the definition is logic, if we say the OVS, right? OVS is another type of network elements. It's running on CPU. All right? So this device, this type of device, if we put them together, it becomes overlay network, right? This is still, belong to physical device, but it's just running on CPU side. The logical device is different than that one. Logical device, we call it logical device because it's logically in there, but the implementation point could be on the CPU, on the OVS, or could be on the physical switch. From user perspective, they don't care. So where it's running depends your endpoint. If your endpoint is attached to the OVS, well, there is one OVS running in there, one attachment point in the OVS, but another port is attached on the physical network in somewhere. So we create paths to connect them together. So logically, they connect together becomes a logical switch. So the port could be everywhere in the network.
Yeah. Yeah.
Okay. A router is the same concept. So physically, don't know, it's distributed in everywhere. But logically, you see from service perspective, I only see one logical device. Router or switch, they are port in everywhere because this is what, as a network user, this is what I want. I don't want to touch to what kind of topology, what kind of encapsulation, and what kind of fabric you are using. I don't care. From service perspective, I only care my services. So this is the logical device concept.
So that includes virtual.
Yes.
You never use the word virtual.
Virtual, because I try to eliminate the confuse. could be virtual, because if I use the same words as virtual switch, you are confused with currently the virtual switch running on the CPU, running on the server.
I think
right.
let's run the demo first. But after the demo, if you still have
they
questions,
are different. Conceptually,
give you more.
They are different.
Okay.
This is a logical in there, but physically could be several OVS that connected together becomes a logical switch. All right.
Okay.
So this is another levels
we can
abstraction.
Run a demo maybe. Let's do a demo first. If after the demo you still have questions, we can answer. Yeah, I think that's give you more the tangible way to explain that. So I have a setup. I'm using MiniNet to set up some OVS topology. This is MiniNet topology. We created 6 OVS instance that we attach a bunch of endpoints to the switches. So first, let's run the controller. So that's the feature required for this demo. So this script basically creates the MiniNet topology I just showed you in that previous slides. That shows you all the endpoints and the logical switch we create using MiniNet. That creates that physical topology. So now we're gonna create the fabric, which does the abstraction. So when we create the fabric, we attach the fabric provider code, the implementation within the fabric. Okay, so that script basically create the first fabric, which consists of the first 4 switches. It's a VXLAN type of fabric, as you can see the attributes. It's a VXLAN. It consists of 3 switches, and also it captures the physical topology. So on that fabric, so first let's demo the single fabric. On that fabric, we create 3 logical switch and connect a few different endpoints. So then we those windows we log into each different endpoints. So before we create the logical switch, we haven't connect them using layer 2 yet. You can see the data path is not working. So now we run the script to create the logical switch, as in that. So now you can see once it's interconnected with layer 2, within that subnet, all the traffic going through. So now we're going to create a logical router, connect those 3 logical switches. So then you can have traffic across different subnet. So we log into different subnet, 35, 36, 37. So we ping across different subnet before we create the logical router. You can see the traffic doesn't go through. So now we run the script. We create the logical router which connects the 3 logical switches we created before. You can see the traffic between all the subnets going through. So then we create another. We could create another logical switch, 3 logical switch on different fabric. We create a fabric 2. So we have 3 endpoints. Each one connect to 1 logical switch. So this is just similar to what happened on the fabric 1, on the first fabric. So the point is we can demonstrate the cross-fabric interconnection. So now before we create the interconnection, we log into the endpoints on different fabric 1 and fabric 2. Okay. Okay, now we're going to create the interconnection. So pay attention, those logical switches on different fabric right now. Yeah, so right now, if you ping them, because you don't have the interconnection created yet, so the traffic doesn't go through. So now we created the interconnection. Basically, it's layer 2. So you can see the endpoints, although they are on the same subnet, but physically distributed on different fabric, they can go through from the 35.2 and to 35.8. So this demo, we're going to show how to interconnect the logical router which on different fabric, just as I mentioned in the slides. So internally, right now, underneath, we're using layer 2 to interconnect those layer 3 constructs. So before we create that interconnection, you can see the layer 3, if you have subnet across, if you have different subnets, which are on different fabrics, the traffic doesn't go through. So now you run, now because you run the interconnection, the traffic, you can see the ping going through. So this demo shows you if you have external, if you need to communicate with external network with some different IP domain, for example, public IP domain, and you have private IP. Here is the example, 182.168 is public IP, and the 10.0 subnet is private IP. So you can just create the IP mapping using the FaaS offered services on the port. So the host X, this window, represent the external endpoints which are on different IP, the public domain, and that one 35.8 on private domain. You can see. So before we run the you see, yeah, we created the IP mapping using mapping that private IP to the public IP, so the traffic can go through. So using just those APIs, you see, you don't have to really know what's with underneath. It's OpenFlow or it's VLAN based or VSLAN based. It's very simple to build a logical switch and program them. And the model, as I said, maybe not complete. We're going to keep evolving. But I think we are stepping into the right direction. I think that's concluded my talk.